All right, 3P and 4 students, I'm now going to continue lecturing. In order to do assignment 5, one of the first questions you'll find you need a section from chapter 4. So we're going to review section 4.8, which talks about band-to-band transitions. So if you look at the valence band and conduction band, you can plot E versus K, and in that diagram, the recombination of an electron in the conduction band and a hole in the valence band can occur at the bottom of the conduction band and at the top of the valence band. And in that case, E equals EG, or delta E equals EG, equals HC over lambda. And so therefore lambda G equals HC over EG. So that becomes the expected wavelength of the emission of a photon from that transition. However, the transitions that could occur can be from higher states in the conduction band into lower states in the valence band. That means that the emission wavelength will actually develop over a range of wavelengths, and we can no longer define it as a single wavelength. And as a result, the emission spectrum of an LED will have a certain spectral width, and it will correspond to a certain range of photon energies. So the purpose of this section is to figure out what you would expect to find and predict the width of the spectrum and the shape of the spectrum based on this band model. One of the things we're going to assume is a direct gap transition, which means that the K value or the momentum value of the electron is not changed when it recombines with the valence band. And we discussed that in class because the photon carries away practically no momentum, or very, very tiny momentum, which is insignificant in terms of the scale in this diagram. We can assume that the transitions are going to be vertical. So the first thing we're going to do is to assume the parabolic model for a conduction band and a valence band. Keep in mind that the parabolic model is simply the well-accepted approximation of the true shape of the curvatures of these bands. There's nothing built into band theory that says they have to be parabolic, but especially if we're only modeling them near the bottom and near the top of the bands, the parabolic assumption is usually very adequate. So we're going to now write the equations. E sub E equals E sub C plus H bar squared K squared over 2me star. So that is the parabolic shape of the conduction band. And then E sub H equals EB minus H bar squared K squared over 2mH star. So we have the expression of both the conduction band and the valence band shapes. Now the transition energy E as a function of K is equal to the value of h nu, and that's going to be E of K minus E H of K. In other words, on this diagram, whatever value of K we're at, so let's say we're at this particular value of K, at that value of K, the transition will occur between this state in the conduction band and this state in the valence band. So that transition energy E of K depends on the specific value of K where the transition happens. Now, if you substitute the shapes of these band structures in here, you can show that this is equal to EC minus EV plus h bar squared k squared over 2 ME star plus h bar squared k squared over 2 MH star. All I've done is taken this term and included it in the expression. You can rewrite this as EG, because of course this part of the expression is just equal to EG, plus another term, which we call h bar squared k squared over 2 mu, and we call mu the reduced mass. And the relationship between mu, me, and mh is 1 over mu equals 1 over me star plus 1 over mh star. So if you make this substitution, this will become an algebraically correct statement. So the issue now is how do we make sure that we get the correct spectrum of emission? The emission spectrum is going to depend on the electrons that occupy the states in the conduction band, and it's also going to depend on the availability of holes in the valence band to accept the electrons that recombine. So there's two things we need to know for the probability of all these different transitions taking place. One is we need to look at the density of states. And then the second thing we have to look at is the Fermi-Dirac distribution function. So we need to know both the density of states in the bands, and secondly, the distribution function to tell us if the electrons occupy those states and if the holes are available in these states for the electrons to recombine with holes at varying values of K. So you can picture this diagram in a bit more detail, and I'll sketch it more or less the way it's shown in the book. I'm going to redraw this diagram a little bit more clearly. We're going to consider a range of K values, which we can call delta K. So over that particular range of K values along the K axis, we're going to consider a range of energy values along the energy axis in the conduction band. We can call that delta E sub C. And we can consider a range of energy values in the valence band, delta E sub V. So you can see that over this range of K values, you can get photons which could have as small an energy as from here to here, or the photons could have as large an energy as from here to here. So there's a range of photon energies that can be produced by a range of K values along the K axis. And the size of that range really depends on delta E versus delta K in the conduction band, plus it depends on delta E by delta K in the valence band. So we really have to add together the delta E values in the conduction band plus the delta E values in the valence band to get the entire range of energies that can produce, which will represent the photon energies that get produced by that range of K values. So mathematically, we can look at the density of states that exist in the conduction band and the density of states that exist in the valence band, and we can actually essentially add together the ranges of energy in each of those bands. We already have added the range of energies in each band by the equations which we've written down over there. So we'll now look at the density of states which is now called the joint density of states. Remember, we have a density of states for the states in the conduction band that tells us the number of electron states per unit energy range in the conduction band. And we have a density of states for states in the valence band. But what we really need is the density of states where we add these two bands together. So the joint density of states is calculated using the values of E, in which we already added together the energies in the conduction band plus the energies in the valence band. So that will become our joint density of states. And before I write down what the joint density of states, I'll just remind you of what the density of states is for a single band. This would be 1/2 pi 2me star over pi squared h bar squared to the 3/2 times E minus Eg to the 1/2. So that's the expression for the density of states, which you would have learned in 3FO3, and we've used it in this course a couple of times. The change we're going to make when we look at the joint density of states is, instead of just considering me star, we're going to consider the density of states relevant to this new quantity we're calling E of k, and it looks just very similar to the original density of states, to the original band, except in place of me star or mh star, it contains this quantity mu, the reduced mass. So the joint density of states is equal to 1/2 pi times 2 mu over pi squared h bar squared to the 3/2 times E minus Eg to the power 1/2. So if you compare this joint density of states, it's really the same as the original density of states, except we've used mu in place of me to account for both the density of states in the conduction band and in the valence band at the same time. So that joint density of states now needs to be combined with the probability of occupancy of the states. And the Fermi-Dirac distribution function is approximately e to the minus EC minus EF over KT. Now this approximation is valid providing, I'm sorry, I'm going to clear this up. This approximation is valid provided EC minus EF is much greater than KT. So it's valid so long as the Fermi energy is reasonably far from the bottom of the conduction band or reasonably far from the top of the valence band. Now, in the conduction band, this is the probability of occupancy of states. In the valence band, what's interesting for us is really 1 minus f of E. We really want to know the probability of a hole existing in the valence band. And that is therefore, if you take this and subtract it from 1, you'll find you get this expression. So if you substitute, instead of the conduction band, you substitute the valence band, you'll have the density of states associated with the valence band, and you'll end up with a plus sign in the exponent rather than a minus sign. You can try that out for yourself. In other words, take the Fermi-Dirac distribution function in the valence band and then simply subtract it from 1. If you want to review this, this quantity here is in chapter 2. This quantity here is also in chapter 2. So if you want to review these expressions, they're covered and introduced clearly in chapter 2. Now, once you've gotten these two quantities, the density of states in the conduction band and the Fermi-Dirac distribution in the conduction band and in the valence band, and by the way, I made a typo, that should be E sub E. That's the energy of the electron minus EF. This is the energy of the hole minus EF. Once you've got those expressions, you can put this all together to figure out the probability of an energy at a given value of K. So this expression, f of E times 1 minus f of E, the product will be something that represents both the probability of an electron in the conduction band at a given value of K multiplied by the probability of a hole in the valence band at a given value of K, which is given by this expression. If you multiply these two expressions together, you will get the probability of both the electron being available and the hole being available, which will lead us to have a transition or not. So if you multiply these two quantities together, you'll find that that is equal to e to the minus E over kT. Of course, if you want to finish this, you have to include both the density of states, the joint density of states, which we have here, as well as the product of f of E 1 minus f of E. If you put all that together, you will get what's called P of E. P of E is equal to, or is proportional to, d of E minus Eg multiplied by f of E times 1 minus f of E. So we have here an expression for what we call the probability of a transition. The probability of the transition is the product of the density of states for that range of K values, multiplied by the probability of an electron in the conduction band times the probability of not having an electron in the valence band. So we can put all that together. So we're going to combine this equation here and this equation here. You can see here we have an E minus EG in that expression. And from over here we have an exponential function. So we have P of E is proportional to E minus EG to the power 1/2 times E to the minus E over KT. So I've taken this term out of the density I've taken this term out of the joint density of states function, and I've taken this term out of the Fermi Dirac distribution function, and I've used those terms only. I've neglected all these other numerical values because we're just doing a proportionality here. And this is the probability of a transition. And we can call the photon emission rate. It's really a new name for the probability of a transition. And the photon emission rate is proportional then to E minus EG to the power 1/2 E to the minus E over KT. So you can plot that photon emission rate and that plot looks something like this. First of all, there won't be any photons emitted below the energy gap. So below EG, there are no states, there are no photons. As you exceed the energy gap, the emission rate will rise quite quickly, and the rise here actually is due to a density of states. Which increases. Remember, the density of states increases as the square root of energies exceeding the energy gap. So that square root increase in the density of states is really the shape of this curve. This should be proportional to the square root of energy. But then as you go up to higher and higher states above the energy gap, the probability of an electron occupying the state and the probability of a hole in the valence band will decrease. And you get a curve here that really follows the probability of occupancy. So as the probability of occupancy dies away further up into the bands, the probability of a transition also dies away. So you can see that there's a certain energy which is at the center of the transition, where you get the maximum probability or the maximum photon emission rate. And that maximum photon emission rate would determine the peak wavelength of an emission process in this problem. So there'll be a certain peak wavelength, and you can always convert energy into lambda. So once you have an energy distribution function, which we've derived here, you can also convert it into a distribution function of wavelengths, lambda, and you'll find that lambda produces the intensity of radiation increases to a maximum at a certain wavelength range, lambda. And on this energy side here, there'll be a certain maximum wavelength, which corresponds to lambda sub g. So that's the wavelength at the energy gap. And then the wavelengths will get shorter and they'll die away. So as the wavelengths get smaller, the photon energy gets bigger. So you're starting there at the band edge and traveling to the right. In the case of wavelengths, you start on the right and you're traveling to the left as you exceed the band gap of the semiconductor. So I would have loved to give you this information in person. It does take some thought. So please read section 4.8 and spend some time trying to digest these equations. They're not that complicated, but they do require some thought. There's one other extension I'd like to make here, which is for a solar cell. We discussed solar cells fairly briefly, and we discussed the fact that a solar cell absorbs radiation. So absorption in a solar cell. Of course, in an absorption process, an electron in the valence band is excited up into the conduction band by a photon, which arrives. We made a plot where we plotted the absorption coefficient as a function of energy, and we showed these curves that look like this for various semiconductors. The absorption would occur for wavelengths, lambda below a certain wavelength, and it would not occur for wavelengths above a certain wavelength. So this would be lambda sub g, which is the lambda associated with the energy gap. We can now predict the shape of the curve, the shape of the curve for the absorption coefficient. The shape of that curve will be dictated by the density of states function. So it will actually look the same as this curve here. It won't contain the probability of occupancy though, because when a solar cell absorbs a photon, the photon that you're absorbing will determine the probability of occupancy. It's not determined by Fermi-Dirac statistics. So for that reason, in a solar cell, the absorption rate will look just like the emission rate, except it'll just contain the shape of this density of states part of the description. So therefore, absorption is proportional to E minus Eg to the power 1/2. The absorption as a function of wavelength is going to be proportional to E minus Eg to the power 1/2. And that distinguishes it from the emission spectrum of a solar cell. So we can also write that this way. Where hν is the photon energy for the solar cell, Eg is the energy gap, and the shape of the absorption curve is predicted to be like that. If you then convert that into a wavelength, it would look like this, which is the diagram in chapter 5, which we looked at for various semiconductors. So I will stop discussing chapter 4 at this point, and in our next section, we're going to cover, we've already covered the LED. In our next lecture, which I'll give you in a couple of days, we'll start talking about the transistor, which is the last chapter. The last chapter, chapter 8, covers the bipolar junction transistor and it also covers the junction field effect transistor.